be a steel ball. For ball bearings, smooth, glowing, and hard. A symbol of perfect form, but also a symbol of the precision of all ball, roller, and needle roller bearings. Deviations from the theoretical ideal geometric shape may be as minimal as 1/100,000th of a millimeter. The raceways of the rings where the balls, rollers, or needles will ultimately have to run have also got to be more precise than the human mind can even imagine. This means elaborate, painstaking care is taken with the raw materials, so that their chemical composition, carbide size and distribution, austenitic grain size, cleanliness, and hardenability are all what they should be. And these are only the most important properties. Nor do we want to discuss the vast array of meticulously worked out manufacturing processes. And in series production as well, we're still talking about hundredths of a millimeter. Measuring, testing, checking. It's all an integral part of the rolling bearing industry. Right from the outset, it has always owed its life to the precision of its products. In the final analysis, this precision has a major influence on the quality of the machines, vehicles, and other equipment in which the ball, roller, and needle roller bearings are installed. The ongoing yet silent improvements of the standard bearings with regard to load carrying capacity, insensitivity to tilting and wear, uniform high production precision, all the way to endurance strength, are only of any use when the bearings are properly installed. So, how the bearings are mounted is decisive. Expert professional mounting is always called for. This is no high science, even if the rolling bearing manufacturers sometimes give that impression. But it is top quality craftsmanship, nothing less. Mounting actually starts with proper warehousing. Here too, the skilled installer cannot afford to do things by halves. After all, he's the one who'll have all the hassles with sticky or rusty bearings. Which means we start by paying close attention to the temperature and humidity in the storage facility. The bottom line here is that this facility must simply be as clean, as dust-free, and as dry as humanly possible. The start of the mounting process couldn't be less dramatic. When the designations on the parts list and the package the bearing came in have been compared, when the inventory is correct, when all the parts have been deburred and cleansed, that's when the measuring procedure begins. It may be a crashing bore, but it has to be done. Basically, both the rings and the rolling bearing should be well supported by their seating surfaces. This, however, may often complicate installation or even prevent the floating bearing effect. And if the rings are mounted too tightly, we'll find ourselves crowding a bearing's radial clearance. A good rule of thumb is, if the inner ring revolves, then it should be tightly fitted. If the outer ring does the revolving, then that's the one that gets the tight fit. This is all the designer's job. The installer, on the other hand, has to check whether the specified tolerances have been adhered to. There are all kinds of doohickeys for this job. They work either with absolute display or as comparative gauges. There are a fair number of rolling bearing models, and even more sizes. This is why the mounting techniques vary as much as they do. When deciding on the installation method, it is important to know whether or not the bearings can be taken apart, and whether or not the bearings have a tapered bore. This is a deep groove ball bearing, and in this example it stands for all the bearings that cannot be taken apart, which in other words have to be mounted, so to speak, in one piece. And here we can see a cardinal error. The often considerable mounting forces must never be transmitted over the rolling elements. The rolling elements would then press into the raceways, sending the bearings straight to the scrap heap. This is the right way to do the job. When the inner ring gets the tight fit, then you direct the mounting pressure through the inner ring and only the inner ring. This press makes the whole operation elegance itself. An experienced installer can also put small deep groove ball bearings in place with a mounting sleeve and a hammer, but it would never enter his mind to hammer directly on the hardened bearing rings, and he would always make sure the mounting sleeve or cap is not larger than the bearing ring he wants to mount. You can also heat up the bearings in an oil bath, in a heating cabinet, or on a heating plate. Remember, the temperature mustn't be any higher than 120 degrees Celsius. That's 248 degrees for you Fahrenheit freaks. If you get the bearing any hotter than that, you could damage the material structure. It's quicker, safer, and cleaner to use inductive heating devices to bring the bearings to mounting temperature, even if those bearings are sealed or greased for life. Larger and heavier bearings can also be inductively heated. Temperatures as low as from 80 to 100 degrees Celsius, that's 176 to 212 degrees Fahrenheit, will give the bearing sufficient expansion. And as an extra added attraction, the heated parts are automatically demagnetized. Careful though. If they aren't quickly pushed into place without being tilted, they'll shrink too soon. Then you'll find yourself with the bearing right smack in the wrong place. Dismounting calls for a lot more energy than mounting. Fretting corrosion tends to build up after longer running periods. You should always apply the extraction tools at the ring to be removed, especially if you're planning to reuse the bearing. The job is easier if the designer thought to provide you with withdrawal grooves or some such features. Then you can apply the extraction tool directly on the tightly fitted bearing ring. If this is not the case, then you need equipment that will allow you to grip the raceway between the balls and the cage. Master these extraction techniques and you will soon find yourself profitably moonlighting as a dentist. The consequences of unprofessional mounting, Brinell marks on the raceways, which come about when the mounting or dismounting forces are directed through the rolling elements. When dismounting, the extraction forces must always be applied to the tight-fitted ring and only that one. This all goes much smoother with the hydraulic method, especially on larger bearings. You simply inject oil into the grooves and bores between the shaft and the bearing ring. The extraction forces can be reduced to 1/10 of their original level, and damage to the fitting surfaces is avoided. Cylindrical roller bearings can be taken apart. Depending on the type, you can detach either the inner or the outer ring. Both rings can also be individually mounted, which makes mounting and dismounting a whole lot easier. The same thing, of course, applies to similar types of needle roller bearing. But tapered roller bearings can also be disassembled, which is a fancy way of saying you can mount the inner and outer rings separately. When you cold mount small rings, everything we already said still applies, and you use the same equipment as well. You do this job much better and be kinder to the fitting surfaces in the process if you heat the ring and then shrink it on the seat. You can do this here as well with a heating plate, an inductive heating device, or an oil bath. Forgive us for repeating ourselves, but it's important. Never get it any hotter than 120 degrees Celsius or 216 degrees Fahrenheit. In this example, we're shrinking the inner rings from 2 cylindrical roller bearings onto the axle journal of a rolling stock wheel set. The outer rings with their roller and cage assemblies have a sliding fit in the housing. A couple of taps with the plastic hammer, and on she goes. Pressing out is no different, nor is there anything new about the extraction process. If there are no withdrawal nuts available, you can remove tapered rolling bearings, for instance, with a special extractor, which grips between the rollers and the guiding lip. Individual small rings can be dismounted with a heating ring. This aluminum ring is heated over a heating plate. Then it passes the heat along to the inner ring. This expands it and makes it easier to remove. When, however, cylindrical rolling bearing rings, especially the big ones, have to be fitted frequently and in large numbers, then an inductive device really pays off. This will heat the ring to be dismounted so quickly that very little heat is transferred to the shaft. This makes removal of the inner ring from the shaft seat child's play. But let's not play around with open flames. Rolling bearing rings are sensitive to non-uniform heating and localized overheating. If push comes to shove, you might heat larger rings with a ring burner. It's certainly nice to be able to mount the rings on cylindrical roller bearings individually, but this is not without certain hazards for the bearing. Should the rings or the roller and cage assemblies get tilted during installation, you're likely to get score marks. This surface damage then becomes the point of departure in subsequent operations for flaking, which in turn, you guessed it, will qualify yet another bearing for early retirement. One more thing about tapered roller bearings. As tapered roller bearings can only carry thrust load in one direction, you normally need a second bearing in a mirror image arrangement for counter guidance. For simplicity's sake, we've put the 2 bearings right next to each other here. You will doubtless not be surprised to discover that the bearings in X arrangement form a distinct X, and the O arrangement an O. You'll find the X arrangement in this spur gear transmission. As the axial and radial clearances of tapered roller bearings are established during mounting with an adjusting nut, a cover, or by inserting fitting washers, the rings are usually given a loose fit. The mounting forces are respectively low. This means small tapered rolling bearings will not cause any installation problems. Dismounting could be rougher. This means you'll need some dismounting gadgets. Here, the extraction force is applied to the large lip of the inner ring. We're only mentioning thrust bearings such as single or double-acting thrust ball bearings for the sake of completeness. As they normally have an adhesion seat on the shaft washer and always have a loose fit on the housing washer, mounting and dismounting them is a real piece of cake. Needle roller bearings in a wide variety of combinations and permutations are also a part of the FAG catalog. These bearings are installed wherever high load carrying capacities at low section heights are required. Needle roller and cage assemblies are just what the doctor ordered for space-saving and lightweight constructions. There are also bearings with tapered bores. They either sit directly on a tapered peg or on adapter sleeves and withdrawal sleeves, which in turn sit on a cylindrical shaft. Small bearings can be pushed onto the tapered seat with a lock nut. Small bearings with adapter sleeves are pressed on with an adapter sleeve nut. Small withdrawal sleeves are pressed on with the lock nut between the shaft and the inner ring. This operation is a whole lot easier with so-called hydraulic nuts. They are available for all standard sleeves and shaft threads. They are made up of a ring body with an internal thread and a hydraulically operated rotary piston. But regardless of what installation method you may use on bearings with tapered bores, one thing is always essential. The inner ring always expands while it is being pushed onto a tapered seat. This reduces the radial clearance. All of this was taken into advanced consideration by the bearing manufacturer and preserved in tables so that the clearance reduction provides a measure for the seat character. This is why an experienced installer will always measure the radial clearance before mounting and check the clearance while pressing the bearing onto the taper. Always in the balanced zone and always across the entire bearing width. Instead of measuring the radial clearance decrease, you can also measure the displacement on the taper. There are also tables available from the manufacturer for this calibration. Fitting and securing the retaining nut is a routine proposition, which we're only mentioning so you can't accuse us of not mentioning it. Here, during installation of the mounting sleeve, the bearing is moved across its oil film by a nut with pressure screws. This diagram clearly shows you how this process works. Pressurized oil is fed between the sleeve and the bearing. The oil film largely eliminates friction between the mating parts, which means the bearing can be displaced onto its seat without significant energy requirement. The mounting and withdrawal sleeves are mass-produced, starting at diameters of 160 millimeters, or a little more than 6 inches, and supplied with the necessary oil grooves and feed ducts. On smaller self-aligning ball bearings, the radial clearance normally cannot be measured with measuring tools available at the mounting site. The self-aligning ball bearing should be pressed onto the sleeve with the sleeve nut. The ring must be able to rotate freely in the circumferential direction. The nut is moved up with one of these torque wrenches and then tightened with a defined distortion angle. You can take the torque and distortion angle from the tables. Basically, construction with rolling bearings is almost always simple and uncomplicated. Nevertheless, people are always making the same mistakes. If you fit a radial bearing too tightly, for instance, then its radial clearance is completely removed. The rolling elements will run under detrimental preload across the entire circumference. Differing thermal expansions will bring about the same effect. The warning signals are clear. Whining or high-pitched running noise, elevated operating temperatures raised even higher by detrimental preload so that the bearing soon fails because of running hot. An outer ring looks like this. The rolling tracks run over the entire circumference, even on a ring only subjected to point load. Bearing rings are relatively thin-walled. They adjust their shape to the shape of the mating structure, even if that structure is oval. Under certain circumstances, however, they are so badly deformed that zones of excessive radial stress are created. This outer ring, for example, is part of a self-aligning ball bearing which landed on the junk heap before its time because of oval deformation. When the seats of non-aligning bearings reveal large misalignments, then a so-called detrimental misalignment preload takes place. The inner and outer rings are tilted against each other. The rolling elements then run under inner restriction in the apex zone. One characteristic of this phenomenon is a diagonal groove on this stationary ring. Axial preload comes about when the rings are too tightly adjusted during installation, when the axial clearance is eliminated because of thermal expansion, or when the outer ring of a floating bearing is unable to move because it was too tightly fitted. If worse comes to worse, the bearing ring may wind up looking like this. As we mentioned before, the right lubrication is always important. In fact, more than 80% of rolling bearing failures were caused by improper lubrication. Proper lubrication has a lot to do with the selection of the right greases and oils, but it also means establishing the right filling quantity and relubrication intervals. This is primarily something the designer has to rack his brains over. It's the installer's job to see to it the lubricants stay free from contamination, something we gave some serious consideration when we made our FAG greases. He's also got to make sure they get where they're needed, on the contact areas. The question of which grease for which purpose is no easy one to answer, but there are special rolling bearing greases tested by the bearing manufacturer. This means the bearing manufacturer is also in a position to guarantee them. Arcanol is a name worth remembering in this connection. There's more than one answer to the question, where do we put how much grease? It might be right to fill the bearing and housing cavities with grease. On the other hand, it could be enough simply to grease the bearing, so the excess grease can escape into the housing cavities. As a rule, bearing positions the designer planned for oil lubrication should be filled so that the lower rolling element in the bearing is about half immersed in the oil. This is why you should stop when you've hit the right oil level. More than that is too much, which means the oil would start foaming, a pleasant enough sight on a glass of beer, but somewhat unsettling on a lubrication point. And now a brief word about seals. No, not the ones in the zoo, the ones we use to prevent the lubricant from seeping out and protect the bearing space from exterior contamination. Basically, it's the designer who has to decide whether he or she is going to build in gap-type seals, a few important models of which you can see here, or rubbing seals. It is the job of the installer and the maintenance crew to make sure the seals are properly installed and that worn and unserviceable sealing elements are replaced on regular maintenance runs. This, of course, particularly applies to rubbing seals. We said it before and we'll say it again. The installation of rolling bearings is no postdoctoral science, and certainly no secret ritual. But when you watch experienced, skilled professionals working with material they know inside and out, and observe the habitual meticulousness which marks their every move, you really have to take your hard hats off to these men and women. After all, they're the ones who make sure the designer's ideas are carried out, especially when it comes to the installation of the bearing arrangement. They also bear a large portion of the responsibility for seeing that machines, vehicles, and other equipment function so safely and reliably that hardly anyone ever stops to think where all this safety and reliability actually came from.